Digital code now has the power to cause physical destruction. It can force a heavy industrial robotic arm to shudder to a violent halt, instantly freezing an entire production line in seconds. This is the reality of modern industrial warfare. Assembly lines frozen mid-production, cities plunged into darkness, and automated safety valves disabled, while human lives are at stake. Traditional IT security analysts learn by reading network logs, but in the world of operational technology, or OT, security professionals are forced to learn from twisted metal and mechanical failure. To defend modern infrastructure, we have to look closely at 4 specific moments in history where digital code breached the physical world. In 2003, the SQL slammer worm spread across the global internet in minutes. It had no specific target, and it wasn't designed to attack industrial facilities, but it migrated into them anyway. The worm found its way into the network of the Davis-Besse nuclear power station in Ohio. It choked the plant's monitoring systems, severely slowing them down and temporarily blinding the operators responsible for the reactor. It was a clear demonstration that even untargeted generic IT malware can cripple the sensitive, fragile environments of an operational plant. By 2010, the intent of attackers had evolved. Stuxnet arrived as a highly precise, targeted piece of digital sabotage. The malware injected into programmable logic controllers, issuing malicious commands that pushed spinning uranium centrifuges past their limits, causing them to fracture. While the machines broke apart, the malware fed fake telemetry to the control room. Operators saw normal readouts, unaware of the destruction below. Stuxnet proved that an air gap, an isolated network, was no longer a guarantee of safety. Software code had operated as a kinetic weapon, destroying hardware. The scope of these targets soon expanded to societal infrastructure. In 2015, hackers breached the Ukrainian power grid. The attackers breached the network and weaponized the facility's own remote access tools. They manually switched off substations and dropped thousands of homes into the dark, while the legitimate operators were locked out of their own control systems. Every unsecured remote access point is an active attack surface that can be turned against the facility it was meant to serve. But the most severe escalation arrived with the Triton malware, which targeted something even more critical than power or production. Inside a petrochemical facility, a safety instrumented system, or SIS, acts as the ultimate failsafe to prevent a lethal explosion. Triton was custom engineered to silently disable those exact safety mechanisms. The goal was no longer stealing data or disrupting production lines. The attackers were now deliberately targeting human lives. These 4 disasters reveal a consistent pattern. IT systems are fragile in OT, legacy controllers are easily manipulated, and safety systems are primary targets. The IEC 62443 cybersecurity standard was created as the formalized defense against this specific history of physical destruction. This standard is not abstract theory. Every security control and requirement within it was written in direct response to the specific vulnerabilities exposed by Slammer, Stuxnet, Ukraine, and Triton. Defending physical hardware requires a specialized framework built around these physical realities rather than standard office IT protocols. These case studies show why industrial cybersecurity demands its own distinct discipline. Now that you've seen the attacks, it's time to learn how professionals stop them. Comment Day 8 below to explore the IEC 62443 certification paths you need to secure the physical world.